Hi, welcome everyone to the INNS webinar. Today it will be again a Young Investigator Award winner and speaking about topological learning for vertical domains. This webinar is organized by the International Neural Network Society, and I'm Markus Lewicki, the chair of that webinar. And if you're generally curious about what we're doing, please have a look at our website. You can find it under the barcode. And also for you, interesting to know, this talk will be recorded and you can later on also watch it on YouTube. What's way more exciting is, of course, you can hear, listen, and at the end ask some questions. Before we hand over to Kwon Min, I wanted to motivate it a bit, and I can actually very much relate to that topic, even though I'm not a researcher in graph neural networks. When I was doing my PhD in the early 2000s, my colleague was working on fingerprint recognition. And in the early times, like when he started beginning working in his PhD, it was very much human feature design and trying to analyze and recognize these. And during that time, they have learned to embed these maybe in graphs and then do a graph-based matching approach. But since then, many things happened. And besides graph embeddings, the next steps were graph neural networks and then graph transformers and finally also some adaptations of LLMs. And I'm quite curious to hear a little bit about what's now the state of the art, because fingerprints is actually quite a simple graph structure, and there are so many much more relevant structures like molecules around. And we need AI that actually is able to capture the underlying connectivity patterns, which are essential for the prediction and for the decision making if we want to use these methods finally in practical processes. And who is better presenting about that topic than Kwon-Min Yao? He was working in this area already for many years, and he is currently associate professor in Tsinghua University, but he also has industrial experience. He was actually the lead of machine learning research in Paradigm, a company with around 2,000 employees. So very exciting experience. And again, this mix of academic and industrial expertise. He got already many invitations for talks, but very interestingly, he was also one of the Forbes 30 under 30, and that's in a huge country of China. So it's really impressive, and I'm very excited to hear more from you. And of course, one of the highlights in his career, as you mentioned, was receiving actually the Young Investigator Award of the International Neural Network Society. And he just shared with me also that besides this exciting research, more exciting times they're happening at the department. They're just launching a new AI department in the university, and many, many more problems also in the physical world have to be solved. He will not talk so much about those now, but stay with us. And at the end of the presentation, we can ask some questions, and after recording, he will still stay with us. We can even ask some more questions. So I'm very excited to hear more from you. Please, the floor is yours.
Okay, I will start share my screen. Many thanks for the nice introduction. Okay.
We do see your screen. There are still some small boxes on top of it, maybe.
Okay.
There's also one on the right, if you can remove that one.
Okay, this one.
Yeah, perfect.
Okay, many thanks for the introduction. And I will talk about, typically, it's a great pleasure to talk about evolving topological learning techniques for vertical domain. So first, I will explain what is the problem, and how, then second, how topological learning algorithms are evolved at the second part. And as the third part, I will pick up drag interaction as a typical vertical domain to show how these techniques can be used to solve those type of problems. Finally, I will briefly talk about future works as perspectives. First, what is topological data in computer science? Previously, I want to use graph instead of topology. But okay, as you can see here, like molecule structure, indeed, we can see it as plane graph or two-dimensional graphs. However, for energy function, the 3D structure or 3D dimension of each atoms can be very important to reflect its real energy. So instead of typically take it as a plane graph, we really need to consider more features. This feature together with this graph structure can be seen as a manifold structure. So in this way, I prefer topology instead of just a plane graph. The same happens for underground networks. So basically, topology is everywhere in real-world problems. However, okay, it's not only everywhere in the world, but it's also particularly in face of large language model. It is especially very important for vertical domains. For example, like financial risk, intelligence analysis. If we want to find a cheater on the transaction network, we need special knowledge, and we also need strict norms. And for biomedicine and healthcare, we typically can only have few samples, but large language model or huge networks, deep networks are very data hungry. So in order to efficiently activate the learning problem of learning ability of underneath learning models, we need to take care of the inductive bias here. The inductive bias here in molecular property is typically the topology inside the molecular data. And last example is about legal judgment. Actually, in this domain, we need some case-based reasoning or logical reasoning. This type of structure can be well represented perhaps by a logic graph. So this is also a very typical usage with topological learning techniques. So with those application background, the strength of topological learning compared perhaps with general deep network or large language model is that first, we can better understand and analysis of topology data in previously mentioned vertical domain. And more importantly, we can provide a solution with better transparency and reliability. So in this sense, let's look at two typical applications, which is frequently taken as test bed for topological learning problems. First is molecular property prediction. So as we can see, GNN is invented about 2016. So since it's born, okay, like GCN and ChebiNet, it is already tested with MPP problems. So with stronger GN, the performance get increasingly improved. And with, okay, since the expressibility of GN can be limited, transformer is taken instead of plain GN as the backbone. So in this way, graph transformer can perhaps get better performance. At the same time, okay, large language models can also get involved. But as you can see, the frontiers, I mean, the best performance at this stage, let me clear screen. Okay, at this stage is not dominated by a large language model. Actually, this shows that large language model can have some intrinsic limitation to consider the topological, the combinatorial exponential underneath the topological data. So the same situation actually happened for knowledge graph completion. The difference is that, okay, the traditional model, the performance can be much worse than large language model because knowledge graph has textual information, and this cannot be well understood by traditional KG embedding model. However, when combined with topological data and underneath graph a textual feature, advanced GN or graph transformer can obtain better performance than plain large language model. So in this way, while classically we perhaps use simple graph learning techniques, now we have language model. But it is still important to design and to use method can be well aligned with underneath topological structure. So in this way, we can see the techniques has evolved in follow this pattern. At a very early stage, okay, we indeed have some raw feature, like graph feature. So I haven't shown this on this timeline. And this is a simple embedding approach, where first make those graph feature transfer graph feature from hand design to those learnable features. And then to GNN, which can not only learn topology structure, but also can take advantage of input feature, like those feature on each node and each edges. And then we try to make the model bigger and deeper. So this is where transformer get involved. And then since the introduce of large language model, we want to introduce some common sense or the ability to absorb textual information. So at this stage, large language model has been combined with the graph to make the learning ability become more versatile. And then since, okay, the fall of last year or the spring of this year, agent become a very hot popular. So previously we deal topology structure. Okay, previously we deal with the topology structure on the data level. And then not on the single model level. And now we deal with topology structure among many agents, which means we try to build up with topology structure between different, among different type of agent. So this is how a topological learning structure get involved, from learnable to versatile, and from data to model, and to many models. With this type of background, now I would like to introduce some works we have done in recent years. I will also follow this pattern. First about KG embedding approach, and then next how to consider a customized subgraph structure in graph neural network. And then next, introduce large language model combined together with graph neural network. Last, I will introduce some recent attempts to learn topology structure between multi-agent system. So this is the first work, AutoBLM. Basically, the concept is that it is an automated bilinear scoring function design framework that searches the best KG embedding method based on the data pattern. So basically, the matrices shown here shows our motivation. This multi is a very famous KG embedding model, perhaps invented 10 years ago. The basic method is that in knowledge graph embedding, we get head, relation, and a tail. So we have a triplet, and then we want to evaluate the triplet can hold or not. So given the embedding of H, R, and T, we need to design a scoring function F to measure the possibility of such triplet. And actually, we show a matrix view of all these works. This is actually 2021, and this is about 2015. And we give a unified view of these works. And actually, this is the embedded vector of R. And in order to get a scoring function, we actually do it in this way. H times the matrix where diagonal elements are filled by the embedding of R, and then finally type with the T. So we can see the H, R, and T are split into 4 chunks. And actually, those scoring functions, the main difference between these scoring functions are the chunks are located into different position of this block diagonal matrix. Basically, in this way, okay, since this multi is symmetric, by symmetric, I mean, if we write T here and H here, the value would be the same because this is only a diagonal matrix. So if we do transportation, then the value would be the same. So in this way, simple E consider a symmetric relation compared with this multi, and the complex EX and analog and the quarter E consider more complex relation in real scenario. So this motivates us to ask one question. Actually, the world is not that perfect. Can we design or locate those trunks in a data-driven way? So this is the question we want to solve. In this way, okay, we want to locate those trunks into different locations of this block matrix. And we want to use validation data. So the search algorithm would build upon a conventional evolution algorithm. The reason why we select evolutionary algorithm because it is a good algorithm to deal with the discrete type of search problem. It contains mutation and it contains crossover. But this is a search problem. When you train the model on the validation set, so it is very expensive. So to speed up the full training process, we need to filter those scoring functions which have bad performance. And we need to rank the remaining scoring function and pick up top 5 or top 3 to train from scratch and then continue the process. To ensure the effectiveness of the filter and predictor, the symmetric property of this or the perturbation invariance property of this matrix is very important. So we design some perturbation invariance feature based on this matrix in order to allow predictor and filter to learn just a few trained data. In this way, this is the performance we obtained. So as we can see, the scoring function we obtain is different from the literature, and the performance is consistently better than previous hand-designed method. And as for search efficiency, we can see the model can be trained in a very fast way. And this is the performance on other type of prediction task. As we can see, previously, this is compared with a simple embedding approach, simple graph neural network approach, complex embedding approach, we still get a better performance. And compare with those, CompoGCN is a very famous graph neural network that's designed for logic graph embedding. As we can see, the simple embedding approach, search embedding model, can still get better performance than typically graph neural networks. So this is the benefit to search a scoring function based on the validation data. And secondly, since embedding model cannot consider input feature, we design some type of graph neural network to further boost the performance. The idea is that, okay, plain graph neural network or simple embedding method like we have told here, and actually it can only consider first order neighborhood. And actually, there is a very famous concept in reasoning on logic graph is that we can have some rule or can have some paths, and this like a chain rule or path can offer extra property or information compared with those simple neighborhood. So in this way, we can see this show an example, like from the spider to sand. Actually, we can have different paths to reach the same entity. And this motivates us to extract, okay, such type of, we call R diagram, and use those R diagram to support logic graph reasoning instead of just rely on first order neighborhood. In this way, okay, for example, if we want to predict whether mother relationship hold between A and B, actually we transfer the link prediction problem into a subgraph classification problem because we will extract a subgraph and use those neighborhood information to support the prediction of this given link. However, if we just extract those subgraphs, we would have many small graphs to be trained. This will significantly reduce our training efficiency. So we designed some special method parsing mechanism to reduce the repeated computation units between overlapping subgraphs. So in this way, our method can still propagate like plane graph neural network, but the propagation path, path will be restricted by what we called here by customized by our diagraph. So in this way, when we reach, for example, here from A0 to F3, the propagation will, this is the 3 hop, will not contain all 3 hop neighborhood from A0, but constrained by some R diagraph from A0 to F3. In this way, we can have focus on related paths and still take advantage of the training efficiency from classical method parsing mechanism. So in this way, we can see the LLM can obtain much better performance, compared with those triplet methods, and also can obtain much better performance than those path-based approach, and also better performance than those subgraph approach. So by use dynamic programming techniques, as we can see, the inference time, our LLM algorithm 1 does not use dynamic programming to avoid those repeated computation. LLM use dynamic programming and propagate just like plane method parsing mechanism. So as we can see, this one, the time efficiency is much better than LLM algorithm 1, and the GRL explicitly extract those subgraphs, so they are not that efficient. This shows we extract a subgraph, but not all paths will be kept. We designed some attention mechanism to pick up those important paths. So as we can see, somehow the design method can extract important information from the big R diagraph. Next, we introduce large language model to work together with above designed LLM. Actually, the basic message is intuitive. This is what Benju has shown in his talk. Like large language model is intuitive and it do implicit reasoning, so it may have some factual error. And like knowledge graph is a very typical way or very famous way to do logical reasoning. And it is deliberative and explicit reasoning. And actually it is work like knowledge base, so it can contain updated knowledge. Our method can be, the framework show how large language model and the graph neural network can be worked together. So basically, you can just take above GN, just add red GN. So intuitive implementation is to use red GN to extract subgraph like this one, from the knowledge graph, and put those important paths or chains, like here, put them on the prompt, and put the attention weight, which means how important the path is as a value here to indicate the importance of this path. And in this way, when there is a KG answer question here, before filling into the large language model, we extract important paths and fill into those prompts, and together with the question, fed into the large language model and finally get the answer. Indeed, in order to make the system work more efficiently, we need more dedicated designs. But how LLM and GN can be work together can be just explained in this way. Just extract some important paths, fill in those paths into the prompts, and then combine together. Okay. Combine together, fill them together into large language model, and then you will get the answer. So this shows the result. As you can see, these are some related works that also try to combine KG with large language model. The reason why DuR can obtain better performance is that RAD-GN can extract more important paths. So as we can see, with those filtered paths and evaluate the path importance, our method can get better performance on those KGQA tests. And finally, this shows how the prompt looks like. So as you can see, this is the original question. And these are the paths extracted by RAD-GN from the knowledge graph. So as you can see, okay, here, this is the path extracted by RAD-GN. We just fill in those triplet one by one as a sequence here. And then this is the attention weight. With those supplementary materials or supplementary information, okay, the final output from the large language model can get more accurate, position. And also, as you can see, the final generated answer can contain some important information from those selected paths. Finally, we try to combine, okay, those topological learning idea with multi-agent system. Basically, the idea is look like this way. Okay, agent act like humans. So if a group of people, they are not familiar with each other, and if they need to finish the task, so they need to learn, they need to know each other, and they need to seek up a solution, not different people to work together. So let's learn from typical organization. If an organization wants to send a group of people to solve a problem for their customers, okay, the company will have some standard operation procedure. And okay, this is standard operation procedure has been designed for multi-agent system, like chain, star, tree, computed graph, layered graph, and perhaps if we don't know, we want to just do some random guess, and this is the random graph. So the basic idea is that we have a knowledge base, and this knowledge base can contain some standard operation procedure from some typical vertical domain. And this standard operation procedure may not be exactly correct, or may exactly fit the current task at hand. So we want to make use of it, but also want to adapt it for the current task. So this is our idea, the main framework. So we will have some predefined SOP in this repository. And then if we have a task, we will pick up some relevant agent. And this agent will be combined with certain tools, like perhaps search on the web, or find some exact data in the knowledge base. And then use this SOP first to guide the collaboration between those agents, and then seek up some output and evaluate the performance. Then we will let the watcher to see whether the performance can be improved or not, and then let the watcher to guide the collaboration between different agents. So perhaps this collaboration is not necessary, so we just stop the connection between this agent and this agent. and between this agent and this agent. So the existing SOP from some vertical domain will warm start the system, and the virtual agent will try to refine the given SOP for the task at hand. So in this way, we can see, okay, this is the performance on travel planner. For the soul planning, okay, it will not involve with the tool usage. So as we can see, while the delivery rate perhaps can be slightly worse, but overall, like common sense or hard constraint satisfaction performance can be significantly improved. And for the two-stage means that we need to use real tool to get like price for the hotel or the price for the airplane. This is more connected with real usage of real usage scenario. So in this way, as we can see, perhaps the delivery rate can still be slightly worse, but those deliberated performance can be significantly improved. And finally, we also have some preliminary result with Gaia dataset. This is evaluation the performance of tool usage. So in order to make fair comparison, we have dropped some significant well-engineered tricks, move those tricks outside of this baseline. And then we evaluated the performance of the tool usage. As you can see, AI evolved, the performance is still much better than compared to those previous baselines. Finally, as we can see, the learning performance, the learning method has evolved from classical, perhaps embedding approach to graph neural network to collaborate with large language model, and then finally to multi-agent system. Now I would show a typical vertical domain where this type of techniques can be a very good choice. So the application we recently work with is drug-related applications, like work with those molecule structure, and those like biomedical network. Today, the focus I will talk about drug-drug interaction prediction. Actually, for this type of application, it is explained in this way. Okay, this is two type of drug, aspirin, and actually I don't know how to exactly pronounce these names. Sorry for that. This is two type of drug. If they are used together, it is likely for the combination need a serious adverse drug interaction. So this adverse drug interaction can perhaps lead to a patient to be in ICU. So it is very serious. It is very serious problem. But however, for this type of problem, if you want to use deep network, there will be a very serious problem, because for deep network, it is usually data hungry. Okay, but for this type of application, it is data sparse. So this means that if we have a learning model which is very expressive, we need to design learning component which can give strong inductive bias. In this way, the learning model can efficiently learn from those few data. So and here actually DDI is a very typical topological learning problem. Let's see this figure. Okay, let's see this figure. This is a drug. Okay. The adverse reduction between two drugs can be seen as a relation type between two drugs. And actually drug can be combined with a certain gene or can be targeted with some virus. So it is typically a topological learning problem. And in drug development, this type of network is called biomedical network. So generally speaking, DDI prediction problem can be seen as a prediction problem on biomedical network. So here shows the technical trend for DDI prediction. This is handle design feature. and this is a simple embedding approach. And this is combined simple embedding approach with hand design feature. And this is graph neural networks. And this is some attempts to use large language model. And the red box shows our works here. So our RapGN can work effectively with just a few amount of data. And the CBR-DDI combine RapGN with large language model. So perhaps the required amount of data can be increased, but the performance is still significantly increased. So let's first start with EmerGNN. This work published 2 years ago and is accepted by Nature Computational Science. And basically, this is our motivation. Okay, we consider emerging drag prediction, which means that this is a drag. It does not have any edges connected to the rest of the drags. Does not have this type of connection. However, okay, since drag is development in a long time and is developed with some purpose, so it must contain some element, and it must have some indication, and it must have connected with some genes. So perhaps we do not have those type of interaction. But let's see, this is a compound. Okay, an emerging drag and a low drag can contain same type of compound. So in this way, this type of shared information between existing drag and low drag can be seen as a weakly supervised information to guide effective learning for those emerging drags. So this is our motivation. In this way, we design a method working this way. Okay, as we can see, this is the emerging drag. There are 2 types of prediction problem we consider here. S1 means a link between an emerging drag and a low drag, or S2, link between 2 emerging drags. So the first way is that we combine DDI network with a biometric network. So this results in a big network. And in this big network, we use previous ideas from RapGN to extract important paths, okay, from the biometric network. So as you can expect it, in this extracted subgraph, it can contain shared gene or shared small compound or the same target symptom in this small subgraph. So this small subgraph will contain enriched weakly supervised information. This type of information can enable, okay, future prediction for those emerging drugs. However, since this combined network is not targeted for DDI prediction, so not all paths can be important. We need to design some attention mechanism to select important paths from this subgraph. So in this way, we contain some special design attention mechanism to find out those drugs, to find out those paths. So this will need to find performance in this way. Okay, let's see. These are some, okay, these are some graph features. And this is simple embedding approach. These are like GN methods. This is large language methods. This is graph neural network, EmerGNN we consider here. So as we can see, EmerGNN can obtain much better performance compared than previous ones. This is how can we combine inductive bias in topology data with those weakly supervised information. And this is an important path we find. Okay, this is the big subgraph, and this is the path with high attention weight. And actually, this path can be found with a strong link correlation with evidence in the existing literature. However, due to time limitation, I will not elaborate this part. but this shows the evidence that those attention weight can reveal some important relation and important paths in this certain vertical domain. And then come to CBR-DDI. Actually, the basic idea is very simple. We perhaps just first turn to this page. In previously dual R, we compare INNS with the large language model. Here, this method is an upgrade of previous method into DDI domain. So first, we still have biomedical network here, and we still have GN here. However, okay, after we extract paths from this node and combined with reasoning with large language model, here the most important thing is that we want to construct explanation for the current DDI task. So this is why we have an extra logic repo here. And we want to use case-based reasoning to create explainable information from the output of large language model. So this way, we will see this figure. Actually, when we try to find why to drag can have certain effect, this is what we will typically see from the literature. So we want to let large language model to generate such type of explanation. And since this type of explanation can be shared among different type of drags, so we use case-based reasoning. In the last step, we use case refine to group those previous explanations and then store them in the logic repo. As performance, as you can see, the performance is much better than those previously question answer in general domain. So as we can see, this is still okay. Previous method included our EmerGNN. As you can see, much better than graph-based one. As you can see, those are direct usage of large language model, very bad performance. And this combined with case-based reasoning, the performance can be significantly improved. And these are the related works try to combine large language model with paths from those biomedical network. However, as we can see, our method get much better performance. And another interesting result is that, as we can see, this is a very large, very big large language model. And this is a very small language model. But the performance, okay, the decrease in the performance is not that huge. So this still means that if we can design a small model can be well aligned with topological data, it can significantly reduce the need of increased parameter size or parameter number. This can be very critical for some application, not here. Here, because the performance or the explanation can be more important, but some more real-time like DDIAgent. Actually, smaller language model can always be preferred because in mobile, we perhaps cannot hold such a big language model in our cell phone. In this way, we can perhaps only have 1B model or even 0.5B model on our cell phone. So in this way, try to design some model can align with the topology structure data can be very important to reduce the need of parameter size. And finally, I would show the case. Okay, this is still the DDI prediction task. And this is the description of the task. And actually, these are the related facts extracted from the knowledge graph. And finally, okay, this is the explanation. We group it from the output of large language model. Finally, I would talk more about the remaining problem in such vertical domain. For example, actually, this is just accepted last week. It is accepted in bioinformatics. Basically, the problem is that, okay, existing work, including our previous work, Actually, a lot of existing work consider the problem that drugs are developed with a certain type of certain purpose. This means that the new drug is not uniform distributed in the chemical space. So this means that there will be distribution changes between existing drug and the new drug. So we want to, but to collect such type of information is very hard. So we want to try to build some simulation framework to simulate such distribution changes between emerging drug and new drug. So this is what we want to do. And this explains our framework. We actually introduce a cluster-based approach to simulate the distribution changes. And these are previously split method like scaffold, low-high, and spectra and data cell. These are all previous work. This work also try to create some distribution changes between different type of molecules, but they are not strongly correlated with drug development. So in this way, as we can see, we sampled a few data, 500 of drugs based on FDS data. We arranged them from previous years to recent years. And we can see cluster give a high consistent index. So this is what we do. We want to create a benchmark to simulate the distribution changes in real scenario. And this is the performance based on our benchmark. As we can see, the first method is that, okay, with distribution changes, the performance can be significantly decreased. And indeed, the performance increased from like EmerGNN with strongly inductive bias from biomedical data, because gene and the disease does not have distribution changes. It is the drug that has distribution changes. So this type of background information can give resistance to distribution changes on the chemical space. So as we can see, the EmerGNN performance can still comparably be good. And like text DDI and DDIGPT, these are text DDI built with GPT-3 and DDIGPT are built with BioGPT-2. So this use much larger text information. So this can contain common sense information. So the performance can still be relatively good compared to those simple embedding approaches. So these are some preliminary message. And finally, as we can see, the performance changes between like major just relation with many samples, few samples, only a few samples. The performance changes a lot. So as you can see, there's still much improvement for currently not only graphical network, but large language model to get more reliable performance on drugs with different type of distribution changes. Finally, I will conclude my talk with future works. So first, on the method level, to be frank, I need to say to learn from topological structure on the data level, there is not much work to do. And since many people or most of people work more with large language model, so perhaps try to find topological structure data inside or above large language model can be a more interesting work for future works. So first is collaboration between in multi-agent system, and then we can also like represent test time scaling as a graph and try to seek a proper graph structure in test time scaling, and like currently supervised fine-tuning or reinforced supervised fine-tuning can be a very good way to improve the performance of backbone. But the reward for the task, like GUI task or many tasks, they are not the chain tasks, they can be graph tasks. So how to use the reward from graph structure cost can be a very important problem. And finally, for vertical domain, like material design, I will also work on in the recent 2 years. Like for drug, they are free molecules. But for molecular design, actually, as you can see, these molecules are structured. They spend in the space. So we need to consider more geometrical invariants when trying to design those materials, and like those climate change. And then finally, financial system, which means we require more controllable inference and more transparent inference from those underneath learning models. And these are some recent works in our group. And finally, these are PhD students and researcher, collaborative researcher in our groups. And that's all for today's talk. Thanks.
Thank you so much for this very enlightening presentations. Yes, wow, of course, a big wall of references there as well. I see there's already a question in the chat. Tosun, do you want to unmute yourself and ask the question directly by yourself?
Okay, I see there is a question on the chat board.
I just want to...
Does dual learning completely solve hallucination problem? I don't see any metric. Okay, this is a very good question. Let's turn back. Okay, let's turn back here. Here. Hallucination problem is a very serious problem in this application domain. Indeed, when we submit this paper to LIPS this year, one reviewer asked us this question. I have to say, hallucination problem is an intrinsic problem in large language model. More or less, it can be reduced, but it cannot be avoided. So in this work, we had used some detector to check whether the generated text here is reliable or not. So the detector on average, okay, give us a score of 0.5. This means it can be reliable, but maybe not 100%. It is, let me try to, okay, it is perhaps 70 to 80% reliable.
Yes, very good. And there is another question, and I will directly add you to the spotlight. Please, go ahead, Pilar.
Hello, can you hear me?
Yeah, I can hear you.
Yeah, thank you, Dr. Zhao, for your presentation. There is a lot of information, and but I would like to know if you have some metrics related to not just to the performance in terms of accuracy, but also something related to the costs of the models. Because I have the idea that these are very costly, not with respect to the comparative models.
Sorry, we haven't considered such metrics yet, but we will consider, thanks for your suggestion, we will consider them perhaps in the future work.
Oh, okay, thank you.
Now, there's always a lot of possibilities to explore. I also have a question because you presented so many different works, and sometimes I was not sure about the consistency in the presentation of the results. I saw, for example, sometimes you showed plots with variance bars. I guess it was variances.
Oh, variance, okay.
In slide 51, it's a variance or standard deviation?
Yes, it's variance.
Yeah. But in some other slides, you highlight sometimes the best results in bold, but were they significantly better, or did you just highlight in bold the best results?
Yeah, it is a good question. Actually, well, we do significant tests under confidence level 95. So if we pass this level, we will. Oh, so there is a typo here. This should be the best. Okay, this should be the second best. So in some cases, we will highlight two best methods, which means they are significant tests we cannot pass 95%. like perhaps not this one, like AutoBLM. Which one? Okay, like these two tied together. And actually, the variance for this data set is very small. It's like 0.000, less than 0.1. So even they only has last one digit difference, this matter still significantly better than ours.
Okay, yes, I understand. There was just I think on slide 45, you have just highlighted in bold.
45?
Yeah,
Okay.
your method, if I understand correctly. There was no significance test, was it? Yeah, 2 slides later. The next slide. Yeah, this one.
I need to have a double check. I'm not quite sure how many experiments are repeated here. Typically, we will at least repeat it 3 times, but I will confirm this with the first order student.
No, I
Many
think
thanks.
you generally do that, and I also generally apply significance tests, and that's very useful. But it's true sometimes when someone else is a first author, it's hard to always check have the control. And I also understand that sometimes, yeah, running experiments 3 or 4 or 5 times requires way more compute, and then we have to think about the dimension of sustainability as well. Coming to this question, you showed how much time the training takes sometimes, but how much energy does it take? Did you measure that? Or?
We will collect this type of
I'm just
statistics.
curious, because I'm personally interested in energy efficiency.
Actually, we care about this when we work with the GNN, but when we transfer to large language model, particularly for this work, CBR-DDI, we use API from NAMA, and so I'm not sure how to exactly calculate the energy consumption if we use API. So I will try to see how to evaluate this, but we haven't done this yet.
No, that's specifically if you run it in the cloud. If you run it on your own system, you can still do something, but if you run it in the cloud, it's getting way more difficult. But it's
Yes.
okay. These things, it's just always this question. We trade off sometimes energy versus accuracy and time, and so many dimensions. But I was just curious. Yeah. Mm-hmm.
Thanks for the suggestion.
Is there any other questions? If you have questions, you can just unmute yourself and ask. There are not too many left now. But I see the hour is also over. So if there are no further questions, I will ask you thank you one more time for this very nice presentation. I'm now clapping my hands here alone, but I'm sure others do the same. It's always quite difficult in the online world to do so. And I will just give a short outlook to future seminars. Let me just quickly adjust. Okay. Yes. Welcome. Thank you again for this presentation. And as we discussed, we will stay online. So I will now in a moment stop recording, but you can still stay a moment online if some others have questions.